5.6 is just a summary of the rest of the stuff that we've done in Chapter 5. So there's nothing new here, but I think it's a good idea to go over this section because we've covered so much ground in Chapter 5. So we'll start off by summarizing what we did in 5.5 in the previous section, even though that should be relatively fresh in your memory. So below we have a flow chart of the different counting techniques that we can use. And we actually didn't even talk about all of these, right? Like we didn't talk about these ones. I guess that's it. We did kind of talk about the rest of them. But anyway, if your brain works in flowchart, right? If you like flowcharts, then you can refer back to this. And this comes straight from your textbook, okay? If you prefer the table that I gave you at the end of 5.5, then you can use that as well. But basically what it comes down to, kind of as we said at the end of 5.5, if you're trying to figure out what kind of counting technique to apply to a certain situation, then really what you need to do is ask yourself two questions. First of all, is repetition allowed? If it is, then use exponents. If it's not, then ask yourself the next question, which is, does order matter? If it does, then use permutations. If it doesn't, then use combinations. Let's practice this. And note that sometimes a single counting problem requires more than one technique. So let's look at a couple examples. This first one says, the Hazelwood City Council consists of 5 men and 4 women. How many different subcommittees can be formed that consist of 3 men and 2 women? Okay. So how many subcommittees are possible? Well, I think we can do this counting by first choosing the men that are going to be on the subcommittee and then choosing the women that are going to be on the subcommittee. So just focusing on the men for a second, we want to choose 3 men. We have 5 men to choose from. And now we can ask our questions, right? First of all, is repetition? And I think the answer here would be no, because it doesn't make sense for the same man to fill more than one. Clearly not allowed here, so we're not going to use exponents. Now the next question is, does the order matter? And here I think the answer is again no, because the people on this subcommittee, it's not like they're filling certain positions, right? It's not like the first person chosen is going to be the president or something, and the second person is going to be the vice president. It doesn't say that. It just says that the members of the committee, the members that you choose are all going to be on the subcommittee. I think we can assume that they're going to be members of the subcommittee in equal standing with one another. So the order in which they're chosen doesn't matter. So since the order doesn't matter, this is a combination problem. So the number of ways I can choose the men is going to be 5, choose 3. Okay. By a similar line of reasoning, the number of ways I can choose the women is going to be 4, choose 2. So that the total number of subcommittees possible is 5, choose 3 times 4, choose 2. I think 5, choose 3 is 10, and I think 4, choose 2 is 6. So you should get 60. So 60 different subcommittees possible. Okay, I better verify that. 5, choose 3. I'm pretty sure it's 10. Let me just see. 5, choose 3 is 10. Yeah. And 4, choose 2 is 6. Okay, so that's that one. Second one says, on February 20th, 2011, the Daytona International Speedway hosted the 53rd running of the Daytona 500, touted by many to be the most anticipated event in racing history. With 43 drivers in the race, in how many different ways could the top 4 finishers occur? So give the video a pause, see if you can figure this out. Here's my solution. I'm going to ask myself the same questions that I did on the previous problem. First of all, is repetition allowed? The answer is no. Okay, it doesn't make sense for the same person to finish both first and second place. Does the order matter? Well, the answer this time is yes, the order does matter, right? someone getting first, well, Lightning McQueen and I don't know, some other racer. Lightning McQueen and other getting first and second is a different scenario than other and Lightning McQueen getting first and second, right? So the order matters here. That makes this a permutation problem. Now, in this permutation problem, we have 43 drivers to choose from, and we want to choose the top 4 finishers. So we're going to do 43 permute 4, which is probably a pretty big number. Let me see, 43 permute 4 is 2,961,840. Right? So lots of different ways that, that the top 4 finishers could occur in this race. Okay, so that's a summary of counting techniques, kind of a brief summary because we didn't talk about very much in that section. But let's summarize our probability stuff now. We covered a lot more ground with probability. So here's a summary. The probability of an event is the total number of ways that an event can occur divided by the total number of possibilities, right? So probability that E occurs is the number of ways E can occur divided by the number of events in our sample space. So this concept came from 5.1, okay? So 5.1 was kind of a brief introduction. And actually, this is called the classical probability, right? So this is called the classical probability. We also talked about empirical probabilities in 5.1. Empirical probabilities are just relative frequencies, right? So it's like if you're unable to compute the classical probability, then what you can do is just go out and collect a bunch of data and then use the relative frequencies as stand-ins for the classical probabilities. And what we learned is that the law of large numbers tells us that the larger your sample size is, the closer your relative frequencies are going to get to your classical probabilities. So it sort of justifies our use of relative frequencies in place of classical probabilities whenever we don't know what the classical probabilities are. And I keep saying relative frequencies, but you should know that relative frequency is just a synonym for empirical probability, right? They mean the same thing. So that was that in 5.1. Now in 5.2, 5.3, and 5.4, we were interested in these kinds of probabilities, these compound probabilities, right? Probabilities involving more than one event. What you should walk away with is that when you see the word or, you should think of an addition rule. Okay, to be explicit, right? Probability of A or B is probability of A plus probability of B minus probability of A and B. If you happen to know that A and B are mutually exclusive, then you can use a slightly easier version of that formula, right? And again, mutually exclusive just means that A and B cannot both happen at the same time, okay? If you see an and probability, then you should be thinking of a multiplication rule. And again, to be explicit about it, probability of A and B is probability of A times probability of B given A. Now, if you happen to know that A and B are independent, then again, we have a slightly easier version of the multiplication rule, right? If A and B are independent, then probability of A and B is just probability of A times probability of B. Okay? So if you see or, you should think addition rule. If you see and, you should think multiplication rule. But I also want you to understand what these probabilities mean, right? Probability of A or B, this is the probability that either A happens or that B happens or potentially that they both happen, right? Probability of A and B is strictly the probability that both A and B occur, okay? Now, this piece of the formula right here, probability of B given A, that's a conditional probability, and we talked about these in detail as well. Remember that what a conditional probability does is restrict your attention so that instead of looking at the entire sample space, here you're only going to look at event A, and you're going to say, okay, if we know for a fact that event A occurs, now what's the probability that event B occurs? All right. Now, when talking about these shortcut rules, the terms mutually exclusive and independent come up, and I'm not going to read this to you. But I do want to just point out that the terms mutually exclusive and independent do not mean the same thing. And so if you want some more detail, if you're confused by that, read through these things and also take a look at this chart where I've provided you some examples of things that are mutually exclusive but not independent. You've got some examples of things that are both not independent and not mutually exclusive, some and so forth, right? So you can read this table to try to make sense of the difference between the terms mutually exclusive and independent. I don't plan on hitting you too hard on it on the test, to be honest with you, but they're important concepts, and they're words that will come up again later on in the semester. If you like flowcharts, then again, your book has a flowchart that helps you to determine what kind of probability technique to use. And so you're welcome to kind of use this flowchart if you like. One of the things that I failed to mention on the previous page was about the complement rule, right? Remember that that the phrase "at least one," the complement of the phrase "at least one" is none. So that if you're trying to compute the probability that at least one, the probability of at least one, then that's the same thing as computing one minus the probability of none. Okay, that may come up, but anyway, let's just practice. Let's just practice a little bit. So example 3 says, in the game show Deal or No Deal, a contestant is presented with 26 suitcases that contain amounts ranging from 1 penny to $1 million. The contestant must pick an initial case that is set aside as the game progresses. The amounts are randomly distributed among the suitcases prior to the game, as shown in the table below. What is the probability? Excuse me. What is the probability that the contestant picks a case worth at least $100,000? Okay. Well, so there were 7 cases that were worth at least $100,000. And in total, there are supposed to be 26 suitcases here. So the probability that they pick a suitcase worth at least $100,000 is going to be 7 out of 26. And that's it. Right? That's all there is to that particular problem. This is just a straightforward classical probability about a single event, right? So it's just the number of ways the event can occur, right, which is 7, divided by the total number of possibilities, right, which is 26. And that's that. Let's look at another example. So it says a card is chosen from a standard 52-card deck of cards. Let A be the event that the chosen card is a 3, 4, 5, 6, or 7. And let B be the event that the chosen card is black. And then we want to compute all kinds of things. But I guess a good thing to do would be to pull up a standard 52-card deck of cards so that we all are on the same page about what these things look like. It's come to my attention that not everyone knows what a deck of cards looks like. Some of you don't play cards for whatever reasons. So let's take a look. So you're welcome to just like do a Google search for like the number of card or the types of cards in a set of playing cards. All right, but here's a good picture. Actually, I can come up with a better one. Here's a good one. Well, that's still bad. I want the picture to not be fuzzy. If I can get it. Okay, can I zoom in on this? No? Let me try. Let me choose another one. This comes from Wikipedia or something. Wikimedia. I should be able to. Oh, wow. Okay. How do I zoom out now? Okay, here we go. Okay. So here's our standard deck of cards, right? So you can see that you have these things are called suits, right? So you have 4 suits, right? You have clubs, hearts, diamonds, and clovers. And then these columns are called ranks, right? So you have 4 aces, 4 twos, 4 threes, right? You have jacks, queens, and kings. And by the way, jacks, queens, and kings are called face cards because they're cards that have faces on them. Okay, so so there's your background information. Let's see if we can answer these questions. So A is the event that we choose a 3, 4, 5, 6, or 7. We want to compute the probability that A occurs. So 3, 4, 5, 6, or 7. Let's see. So 3, 4, 5, 6, or 7. How many of these are there? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20 cards that are either 3, 4, 5, 6, or 7 out of 52 cards in total, right? There are 52 cards in the deck. So we would say 20 out of 52. Okay. Now B is the event that the chosen card is black. Let's see if we can compute probability that B occurs. How many black cards do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So 26 black cards out of 52 cards in total, right? So probability that we choose a black card is 26 out of 52. Now, by the way, we can reduce these fractions if we want, right? 20 out of 52 is the same as 5/13. 26 out of 52 is the same as 1/2. And that should make a lot of sense to you because half the cards in the deck are black and half of them are red. So it makes sense that the probability that we choose a black card is 1/2. Now part C. Part C asks us to compute the probability of drawing a black card given that the card was a 3, 4, 5, 6, or 7. So let's go back to our deck of cards and see if we can figure out what that should be. So we want the probability that we choose a black card given that we've chosen a 3, 4, 5, 6, or 7. So we're ignoring all of the other cards. We're only looking at these cards right here, right? The 3, 4s, 5s, 6, and 7s. So just ignore all of the rest of them. Just pretend that they don't even exist. All right, so 3, 4, 5, 6, and 7s, there are 20 of these cards. And we want to know that out of those 20 cards, what's the probability we choose a black card? Well, out of these 20 cards, 10 of them are black, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability that we choose a black card, given that the card is a 3, 4, 5, 6, or 7, is going to be 10, right? 10 out of 20. 10 out of 20. And that reduces to 1/2. So again, we're getting 1/2 here. And again, that should make sense, right? Because half of the 3, 4s, 5s, 6, and 7s in the deck are black, and half of them are red. Okay. Now, part D asks an interesting question. It says, are events A and B independent? Justify your answer. Are they independent? The answer is yes. The reason the answer is yes is because if A and B are independent, that means that they have no effect on each other. And you can see that that A and B don't have an effect on each other by comparing your answers to parts B and C, right? Because the probability that you choose a black card is 1/2. The probability that you choose a black card, given that event A has occurred, is still 1/2. So clearly, event A does not have an effect on whether or not B occurs, because these two numbers are the same, right? So we say, are events A and B independent? Yes, because probability of B is equal to the probability of B given A. All right, that would be a good justification for the answer. Okay, so there's that one. Now part E asks us to compute probability of A and B. So now we want the probability that we choose a 3, 4, 5, 6, or 7, and that the card is black. So probability we choose a 3, 4, 5, 6, or 7, and that it's black. So there are 10 of those cards, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 black cards that are 3, 4s, 5, 6, or 7s. 10 out of 52 cards in total. So probability of A and B is 10 out of 52. Okay, which reduces to 5 out of 26. Now, I want to give you another way to do that, though, because we said that probability of A and B should be equal to the probability of A times the probability of B given A. Well, let's verify. Probability of A is 20 out of 52. Probability of B given A is 10 out of 20. Notice that you can cross-cancel 20s and you get 10 out of 52, just like we got when we reasoned it out. Okay? So the formula also works for this. It's kind of nice. You didn't need the formula, though. You could have just looked at the cards and figured it out by looking at the cards. Okay. Now, part F asks us, are events A and B mutually exclusive? Mutually exclusive means that the events cannot happen at the same time. So are A and B mutually exclusive? Well, the answer here is no. Clearly, A and B can both happen at the same time, right? You can be a black card and be a 3, 4, 5, 6, or 7, right? So they're not mutually exclusive. So no, a card, we'll say no, a card can be both black and a 3, 4, 5, 6, or 7, right? So the events are not mutually exclusive. Another way to see that is to see that in part E, the probability of A and B was not 0, right? If A and B were mutually exclusive, that would mean that they can't both happen at the same time. So that would mean the probability that they both happen at the same time would be 0. But it's not 0. And so that means that A and B are not mutually exclusive, right? So you say, so no, because probability of A and B is not equal to 0, right? So that's another way to justify your answer. Okay, finally, part G. It asks us to compute the probability of A or B. So we want to compute the probability of drawing a 3, 4, 5, 6, or 7, or drawing a black card. Well, as we've counted, there are 20 3, 4s, 5s, 6, and 7s. But in addition to that, there are other cards that are black, right? So we have 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So in total, there are 34 cards that are either black or 3, 4, 5, 6, and 7s. Another way to count up the same thing is to say, well, there are 26 black cards, but then in addition to that, we have these red cards that are 3s, 4, 5, 6, or 7s, right? There are 10 of those. So 26 plus 10 would be 36, right? Is that what we said before? 36. So we had 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. Yeah, 36. So there are 36 cards that are either black or 3, 4, 5, 6, or 7. So probability of A or B is going to be 36 out of 52, which comes out to 9/13 if you reduce it. Now again, we have a formula for this that we can use, right? Probability of A or B is probability of A plus probability of B minus probability of A and B. Okay, probability of A is 20 out of 52. Probability of B is 26 out of 52. But then if we count up just the number of 3, 4, 5, 6, and 7s, and then count up the number of black cards, then we've double counted the cards that are both 3, 4, 5, 6, 7, and black. So we have to subtract those off to undo the double counting, right? Probability of A and B, we said, is 10 out of 52, right? So there are 10 double countings there. And then if you add that up, sure enough, you get 36 out of 52, just like we got when we reasoned it out by hand. So you don't actually need the formula for this particular problem, but it does work, and it's nice to know that it works. Okay, so that's number 4. One last example. On this example, I think we're forced to use formulas because we don't actually know what the scenario even is. So this one just says probability of B is 0.3, probability of A or B is 0.65, probability of A and B is 0.2. And then it asks us to calculate probability of A, probability of A complement. Now, since all we have to go off of is the formulas, you just have to kind of guess. You just have to guess and see if a particular formula is going to be useful for you. So for example, if I want to find probability of A, one of the formulas that I have is for the probability of A and B, right? I know that the probability of A and B is probability of A times probability of B given A. So, well, this is nice. I know what the probability of A and B is, right? That's 0.2, so I could replace that with 0.2. And I don't know probability of A, but that's what I'm looking for, so it's okay that I don't know it. And probability of B given A, I don't have that, right? I don't have that. So that's bad news. That means that I don't have enough information to use this formula in order to be able to solve for the probability of A. So I'll go on to a different formula. Maybe I'll try to use probability of A or B. The formula for that is probability of A plus probability of B minus probability of A and B. Let's see if I have enough information to use this one. Probability of A or B, we're told, is 0.65. Probability of A, we're not told. I'm just going to call it X. Probability of B, we're told, is 0.3. Probability of A and B, we're told, is 0.2. So this is good news for me. I think I have enough information to solve this. So we're going to say 0.65. I'm going to combine my like terms over here. 0.3 minus 0.2 is 0.1. And now to finish solving for X, I would subtract 0.1 over to the other side. We get 0.55 equals X. So there you have it, right? Probability of A is 0.55. And then part B asks us for probability of A complement, right? So for this one, you're just going to use the complement rule. You're going to say probability of A complement is 1 minus probability of A. That's 1 minus 0.55, which comes out to 0.45. So probability of A complement is 0.45. And that's that, okay? So here's your homework assignment from 5.6, and this brings us to the end of Unit 1. So, so your first order of business is to finish all of the Unit 1 homework, and then once you've done that, you can start preparing for your test.